Hello and welcome to the Titus Timeout Podcast. I'm Jenny Admi-Civi and today we're going to discuss ECM motors in fan boxes. I'm not going to cover the detail of the internal parts of a motor or how they work. If you want to learn more about that, there's probably a lot of good sources online. I want to focus on ECM motors in fan boxes, why they're used, and what the benefits are. ECM stands for electronically commutated motor. So the M in ECM is actually kind of redundant, but you often hear them called EC motors. But since in fan boxes at least, they are referred to as ECM motors, that's what I'm going to call them. The driving factor behind the use of ECM motors is efficiency. ECM usage has gone up significantly since we first introduced them in fan boxes around 1996. Now about half of all fan boxes shipped have ECM motors in them, and many areas require ECM motors for publicly funded projects. In the previous podcast about fan curves, I discussed the minimum and maximum CFM range of a fan box, and I mentioned that when you turn down the fan box SCR, the efficiency also goes down. So let's put some numbers to that. A standard PSC motor is often referred to as a high efficiency motor, but that's actually relative. They may be higher in efficiency compared to older motors, but the fractional horsepower motors used in fan-powered boxes are less efficient than the large horsepower motors used in bigger equipment. For example, a 3rd horsepower motor might be about 60% efficient, whereas the 10 horsepower motor may be 90% efficient. And that's 60% efficient at full flow. As you turn it down, it can go as low as 20% or even into the teens. Okay, so now let's think about a 100,000 square foot building. Let's draw some air handlers on here. Maybe there's 4, and let's say they have 10 horsepower motors in them that we were talking about before. But you have fan boxes for each zone of the building, so you might have them all around the perimeter, and maybe some for the interior offices and cubicle spaces. So now if you look at this, we have 4 10 horsepower motors at 90% efficient, say, and we have, well, let's call it 40 fan boxes at 20 to 60% efficient, depending on where they're operating. So even though it doesn't seem like a big deal for fractional horsepower motors to have low efficiency, the quantity of them in a building makes it worth looking at. So let's take a very basic look at how motors work. Motors work on the principle of magnetism. So let's say you have a simple magnet here. One end is north, one end is south. And inside you have another magnet, but it's on a rotating pivot, and you have north and south. Now opposite ends attract, so the south of the little rotating magnet is pointed towards the north of the big stationary magnet. If you switch the polarity of the little spinning magnet, then it'll actually rotate within the bigger magnet. Motors have a stationary part called the stator and a rotating part called the rotor. So this is a very simple way of looking at how a motor works. By controlling the magnetic field, you can create rotational motion. The ECM motor is often referred to as an ultra-high efficiency brushless DC motor. A PSC motor is an AC motor. It works off of alternating current, which is what it uses to shift the magnetic field that causes the rotation. A traditional DC motor uses brushes and a commutator to work together to shift the magnetic field. If you remember, we called this a brushless DC motor, and it's called an electronically commutated motor, so the ECM uses a microprocessor instead of brushes and a commutator. And this is how it switches the magnetic field to create the rotation. Because it has a microprocessor, it also gives you very precise control of the motor. In standard PSC motors, there's a lag between the stator and the rotor. This is called asynchronous operation. This lag generates heat and is part of the reason that PSC motors have low efficiencies. The precise control I just mentioned in the ECM motor means that it's able to synchronize the stator and the rotor. This eliminates the lag, which is why it has increased efficiency. It also runs cooler. The ECM motor can have efficiencies of 70 or up to 80%, even at turn down. Another benefit of the microprocessor is that the motor can basically control its torque and speed to provide constant airflow. If you remember from the fan curves podcast, as the static pressure increases, the fan box CFM decreases. This isn't necessarily the case with the ECM motor. The ECM motor is pressure independent up to a point, which we'll talk about in a minute. When pressure increases, the motor will ramp up the RPM to maintain the same CFM. Okay, let's scoot this out of the way just a little bit to make a little more room. Now, if you remember from the last podcast, I'd said that a PSC motor had an RPM range of 600 to 1050 RPM. An ECM motor has a wider range. It runs from 300 to 1200 RPM. Once the ECM motor hits 1200 RPM, it will limit itself to not continue to increase the RPM, so it's pressure independent up to this point. But this wider operating range is also a benefit. It means that ECM fan boxes have more flexibility when they're installed. One last thought on the pressure independent operation. The fan box manufacturer has to develop and program the motor for their specific fan box design for this to work correctly, but it's a big benefit. It means that the fan box CFM can be set, and if the pressure conditions change, say filters get dirty or there's more ductwork than originally thought, it will still be able to provide the required CFM up until it hits that 1200 RPM mark. So now let's talk about controlling the motor. Remember that the standard PSC motor uses an SCR to control the motor speed. ECM motor uses a PWM, which stands for pulse width modulation. You might remember we talked about PWM signals in the VAV box reheat podcast. The operation is the same here. A PWM pulses voltage over a duration of time. So say 30 seconds on and 30 seconds off would be the equivalent of a 50% signal. Using a PWM can be the same as using an SCR, where you just use a screwdriver to adjust the output. So let's look at a fan box over a ceiling in an office space. How would you adjust the CFM? Basically, your facility guy, let's draw a facility guy, would need a screwdriver. There's a screwdriver, and he'd need a ladder. So let's draw him a ladder. So now to adjust the box, he has to go find it, climb the ladder, and go up there and make the adjustment. This does not make him happy. The nice thing about the PWM is that you can control it with the digital controls on the VAV box, or the DDC controls. So now he can sit at his desk in his office, at his computer, and control the fan boxes. And this does make him happy. There are a couple of negatives to using an ECM. The first is first cost. Because it has a microprocessor on it, it does cost more than a PSC motor, but this higher first cost is often offset by the reduced energy cost from using the ECM motor. Our studies have shown that the payback can be around 3 years depending on your energy rates. The other negative is that ECM motors have a lower power factor than PSC motors. Power factor is essentially the ratio of usable power to the total power supplied. ECM motors have a reduced power factor, but you can address this with a power filter on the box. And just so you know, Titus does offer the power filter as a standard feature on our ECM fan boxes. So let's summarize. ECM motors have higher efficiency, are pressure independent, have cooler operation, they have no brushes to fail, so they have a longer life. You can control the CFM through the DDC controls. But they do have higher first costs, but lower operating costs, and need a power filter. So now you know all about ECM motors. Thanks for taking a time out with us.